Well, hi everybody. This is just kind of a random little video for a couple different things that I just kind of thought it would be good to share with you all. Every now and then you get some comments from viewers that are really good, and I really want to bring attention to them because I think it's something that will help us all. It helps me, it helps all of us who watch, and I want to give credit where it's due. So, as I was breezing through that video on the SX780 doing the STK module upgrade or update or replacement, that little module, we went over this little schematic of the module itself. And as I was going through, I mistakenly referred to this as the phase splitter. It is not a phase splitter. And you can see there's your bias pot right there. But it would be better for me to I want to read the words of one of our viewers who brought this to my attention. I went right through it and didn't even think. You know, sometimes with me, the wheel is turning, but the hamster's dead. And this was definitely one of those times. So let me just read it in his own words. This is YouTube viewer Pile of Empty Tapes. Okay, so he says at 13:10, 13 minutes 10 seconds, a nitpick. Q5, which is the BD139, is obviously not a phase splitter. It's just a plain VBE multiplier for bias generation. Again, this is your bias adjustment here, i.e. a constant voltage source. A phase splitter is a follower at the bottom and an inverting amplifier on the top, and would be driven from the base. A complementary emitter follower output stage is driven in unison, so it does not require one. If you were to parallel the VBE multiplier transistor with a capacitor, it would keep on working just like nothing ever happened, and potentially make for a better, more wideband constant voltage source. So again, I misspoke, and I don't want to mislead any of you, and I really want to give credit to our viewer Pile of Empty Tapes. Let me tell you something. Your tapes may be empty, but your mind is chock full of good ideas and good thoughts. So thank you, and I appreciate it. Great comment. Another thing is I got a lot of comments referring to the STK modules themselves. And when I made a comment about a lot of them are counterfeit or fake, a lot of you shared the fact that your experiences that you had ordered some modern replacement ones and they had worked just fine. And that is true. First of all, Sanyo Electronics, who holds the patent and who originally made those STK modules, right here, like this one. This is an authentic one, and it was pulled out of an old Yamaha unit. And it's a working one. Sanyo is no longer a standalone company. A while back they were purchased, or they're now a subsidiary of Panasonic, and they have not been producing those STK modules for quite some time now. Now, of course, they made millions of them, and there was new old stock floating around out there for a very long time. There probably still is, but truth be told, it's getting less and less so. Now, there are some other manufacturers, such as Sanken, as one of our viewers, Mark Anderson, mentioned, who was making some legitimate reproductions of them. There's also some of the Chinese ones that are making similar reproductions of them, but they're not exactly the same. There are other ones that are very bad. They're not even close, and if you put them in, they'll fail. And, you know, I kind of wanted to dig a little deeper in this, so I kind of just did a search online for counterfeit or fake STK, and one of the first things that popped up was another YouTube channel named Jordan Pier. And if I remember, I'm going to put the link to this particular video in the more section on this video, because I would kind of tell you to suggest that you watch it. It's very interesting. I was fascinated. He actually took one of these fake ones apart, and I couldn't believe how it was built inside. versus an authentic one. There were also some other articles out there that actually showed an authentic STK module and a reproduction one. And although they were very similar, they weren't exactly the same, but would work. The replacement would work in place of the original. So again, I guess what I'm just saying is buyer beware. You don't know what you're getting, and paying a more expensive price for one doesn't necessarily guarantee that you're going to get a good replacement. You can still get the bad ones even if you pay more. So really the more important thing is look at the reviews, look at how many of them were sold, look at the comments, people that have purchased them, their experiences. Do a little research before you order them, because it is easy to get ones that are fake or that are not up to the standards that you need, especially on some of these older Fisher and Pioneer and so forth, and Yamaha receivers. They really push these things to their limits, and the original Sanyos could handle it. And of course they failed too, but so do discrete components. So that's kind of just, I wanted to bring that up. Now another good comment I received was on the little part of that video that I did concerning making a kind of a repair to a PC board trace using this copper foil. And he brought up a really good suggestion that I had never thought of and didn't even realize, and I think it's awesome. And this is YouTube viewer Sincerely Yours. And let me just read what he says. This is great. He said, the rolls of stick-on copper foil meant for stained glass work are great for PCB land repairs. They're cheap, they'll stick onto your PCB with a bit of rubbing with a flattened popsicle stick or some other object, and will easily withstand the heat of soldering. eBay sells them down to 3 millimeter wide, but you might find them even thinner from electronics repair houses. You could probably make a whole one-off prototype board with the stuff if your design doesn't require very thin lands. So I never even thought of that, but that's another great idea. I mean, I've seen other techniques where people have done kind of what I'm doing, and they've used different types of adhesives to glue it down, but the stained glass stuff is actually adhesive backed, and it is very heat resistant because, of course, when you're doing stained glass and leaded glass, you are soldering on it. So great idea, and again, this is why I love this kind of media. You know, when I was a kid learning electronics, we had a library in town, and we had that same dozen or so books on electronics, and if it wasn't in there, and there wasn't somebody local that you could pick their brain and ask, you pretty much had to figure it out the hard way. Today, there's just so much more stuff available online. Sometimes you can get misled and get bad information, but for the most part, there's a lot of good stuff out there, and it makes it so much easier and convenient to learn things now. So anyway, I just wanted to give those couple of viewers some credit because it was really good information, and I want to share it with all of you. Now, last but not least, this is just something I thought I would do that would be kind of interesting. I've printed out a few sheets of a very common, popular type of transistor called the 2N3055. Now, many of you probably already know about these and have even worked with them and so forth, but I do get a lot of comments and questions concerning TO3 transistors, and sometimes people get a little confused how they work or how they're put together. So I thought I'd just take this couple minutes and go over that. So the first thing I want to bring to your attention is you can go online and you can purchase original from eBay, so-called original, ST Microelectronics 2N3055s. Now, I went on to ST Microelectronics website and I looked up the 2N3055, and you can see it's listed now as an obsolete product. And there's the data sheet. MJ2955 is the PNP complement to it. So that same data sheet has both devices on it. But they are no longer in production. and have not been for a few years now. So if you see them, they're either going to be new old stock that were acquired somewhere, or they're going to be rebranded from another manufacturer, or they're just going to be flat out fake. So, of course, new old stock is the best way to go, because some of them aren't going to be that old and they're going to be original ST. ST is a big company. I forget what S stands for, but the T stands for Thomson. And in the medical imaging field, Thomson Electronics is huge. I mean, they make a lot of the, they used to make a lot of the X-ray tubes, image intensifier tubes, power supplies, a whole bunch of electronic components that are used in X-ray equipment. And they were a big company. Part of their company was acquired by General Electric, I believe, possibly back in the 1980s. I remember it happening. I just can't remember when. But it's still a very large company. They're based out of Europe. And again, this a product built from them is going to be absolute perfect specs. So if you get a 2N3055 original ST microelectronics, be assured that it is perfectly in spec with what the component is supposed to be. As you can see, you can buy these ST logo on them. Okay, the printing's kind of funny looking. That should be a giveaway. But as you can see, I can buy 20 of them for $8.90 American, with the $2.36 shipping. So for 11 or 12 bucks, I can get 20 of these things. I can pretty much tell you they're probably not original STs. They may not even be actual 2N3055s. And we'll get a little more into that here in a minute. If you look at some of these other ones, here's one. Let's skip this one for the moment. There's this one, which is made by On Semiconductor. And this is a big company, and they're still around, and they still make modern products. They're still making these. And you can see the specs on these. Okay? So collector emitter voltage maximum rating is 60 volts. VCER, 70 volts. Collector base is 100 volts. These are the three voltages you want to be interested in. Collector current continuous is 15 amps, okay, and base current is 7 amps, and the power dissipation is 115 watts. And if you do the math, you're going to find out that this is not right. That something isn't going to make sense until you understand what they're talking about. So even though you can have a maximum collector to emitter voltage of 60 volts, let's say, okay, and you can have a maximum collector current of 15 amps. If your collector emitter voltage is 60 volts and you have 15 amps, 60 times 15 is way higher than 115 watts. And the reason being is these are absolute maximum values, but at no time can any of these exceed their maximum. Meaning, if you're running a higher voltage, you have to run it at a lower current. If you're running a high collector current, it has to be at a lower voltage, because it cannot, the dissipation of the device cannot exceed that 115 watts. All right. So if I go to the next page, here's an original ST, and if you look, all of the statistics are the same. Now, here's another one that's a modern transistor that you can find out there, called a 3DD15D. And the 3DD15D looks very similar to a 2N3055. And there is a D version and there is a non-D version. There's one that's 3DD15. The difference is the emitter and base voltages are about half on the one that's 3DD15 without the D. But if you look here, collector current is a maximum of 5 amps, not 15. And the maximum dissipation is only 50 watts instead of 115, less than half. And this is, sometimes they will put out a 2N3055 transistor that has been rebranded, and it's actually one of these. I've gotten them before. Now, when I have things like that, I don't really hang on to them because I don't want to get confused and put the wrong component in something. But I do have an original 3DD15D. And what I've done, I'll show you. So here's the two devices. The one on your left is a 3DD15D transistor. And the one on the right is an original Motorola new old stock 2N3055. And this is one that I've had for a long time. It is an original part. And what I've done is, for the sake of science, I have opened these up so that you can see the differences on the inside of the different TO3 transistors. So if I take this off of here, and I take this off of here, right away you can see a big difference. Let's go through what the differences are first of all. Okay, for starters, let's weigh these things and see what they weigh. So here's the 3DD15D. So it has a total weight of about 9 grams. Okay. And if we look at the original Motorola 2N3055, it weighs 12 grams. It's a lot heavier. Now, you can pretty much see why the weights are so different. If we look at this one, the way these transistors are put together, you actually have that little tiny part right there. That's called the die. That's the actual transistor component itself. Okay, it's not covered. Now, just to give you an idea, this is a little 2N5551, and you can see the size of it. And you see the transistor is relatively, on the outside, looks larger. But if you put the actual component next to this one, they're pretty similar. This is just a plastic case over top of a die that looks kind of similar to this. It's a little bit smaller, but you'd be surprised it's not a whole lot smaller physically. What makes the difference? Well, number one is how the die is made, but also the type of case that it's put in. So if you look here, this metal plate up here is called a heat spreader. And the die is fused either with solder or with a special compound. It is fused to the heat spreader. And then the heat spreader is fused onto the actual base plate. Okay, and I may not be using all the correct terminology again, so I'm just warning you up front. I'm just giving you a description. And you can see the base and emitters wires are right on top of the die, and they come off the die and they go to the pins. So you have your base and emitter pins, and you can see those wires, and they're kind of bent upwards. You see that? And they're very stiff wires for their diameter, obviously. I could push on them and they'll fold over. But you see the machining on how this is done. Now, if you look very close, you can see the material, and you can see the junctions in there. See them? And the fabrication of these is fascinating, how they do it and how they make the P and N junctions and the valence and the doping and all that. And we learned all that in college, and I forgot it because I don't build transistors, but it was very fascinating. Now, let's compare to the other transistor. This is a modern Chinese transistor. And you notice a couple things right off the bat. First of all, there is no heat spreader on this. The die is directly connected to the base plate. And by the way, the other side of the die is actually the collector of the die, of the transistor. So the collector is actually fused to this metal. So this whole metal area here is all connected to the collector of the transistor. So the bottom part of that, whole bottom part of that transistor is the collector. Same thing here, but notice it's not welded or soldered. It's actually glued on with a type of conductive adhesive. You see that? You can also see how much thinner the actual die itself is. The die is physically a little bit wider, or a little bit bigger diameter, I should say, because if you look at them, this one's a little bit smaller diameter die than this one. But if you look how thick that die is and how thin that die is, you can see they're very different. The other thing is, look at the machining of the pins. So you have that blue material, which is your insulator, and the pin is embedded in it. And you can see where they just punched that plate out. It's very rough here. And you can see on this one, the wire is almost touching that rough edge there. It's almost touching on this side too, but it's a little bit further away. And the wire is very, very hair thin, and it is very flimsy. So you have a few problems going on here. Number one is heat dissipation. Number two is when these big wires, when these little thin wires get hot under a heavy load, think about the current. Even at 5 amps, which is what this one's rated at, the accurate rating is 5 amps, not 15, even though some of these get rebranded as 2N3055s. That little wire, when it heats up, it can droop down, and guess what it's going to do? It's going to touch this little punched area, this rough punched area, and you're going to get a short. A lot of times these transistors, when you put them in, you know, you see comments of people saying, I put those cheap transistors in, they lasted a couple days and they shorted out. Well, the die itself didn't necessarily short out. What may have happened is that one of these little wires actually drooped down, because see how much slack there is in them? See how little slack there is in these, and they're bent upwards? See how they're made? So these will bend down, and they'll actually touch that little edge there, and that's your short. So let's demonstrate that. Okay, we're connected up to our little transistor tester, and we hit the test button. And you can see it tests as an NPN. Everything's good. Gain is 70. All looks good. Okay? Now, short circuit on red and blue. And you can see you just barely touch it. Now if I take this little piece right here, a little pointy object, and I just slide it up, NPN, it's good again. And that's what essentially happens to these a lot of times because of the way they're made. And you can see that one's pretty close too. And it doesn't take much, because these are very, very thin, flimsy wires. So I just thought that'd be interesting for you to see. Again, this glue also is an issue because you don't get as good of thermal transfer between the die and the base plate. And this one being fused to the heat spreader and then having the heat spreader connected there, not only does it make the device more rigid, but it also gives more thermal mass to the device, and it ensures that everything stays nice and flat so that when you clamp this down to the heat sink, it'll make good heat transfer to the heat sink. That's why the original the properly built transistors will hold up much better. Again, this is the proper design for an actual 2N3055 transistor. This is not. And again, I give credit to this one because it's not branded falsely. This is how a 3DD15D transistor actually looks. And it's a 50-watt device, and they rate it as such. Where you run into the problems is when this device, and I've seen these, even the big MJ transistors, like the 15035s or something like that, the big 250-watt ones we used. Even some of those, if you buy them real cheap on eBay, it's going to be one of these. It may have a little heavier duty die, but there's still no heat spreader plate. You still have these rough edges and thin wires. It's not the same. And I've even seen, or at least heard tales where some of these, they'll actually take two small dies and put them in parallel on here to rate them at a higher voltage or higher dissipation and so forth. So I just thought that would be interesting for those of you who have never seen inside one of these. And when you always hear, because you hear all these things on the internet and you can't always believe all of them, believe me. But there is seeds of truth to everything you hear online, and fake transistors is one of them. It doesn't mean that everything you order all the time is. It just means that be aware that these things are out there, and when you purchase them, make sure you get them from a reputable dealer. All right, well, just wanted to do that video there. Thought it would be interesting to some of you. And till next time, we're already started on our next project, but I'm not going to tell you what it is. And we'll see you real soon. So thanks again. And thank you, viewers, for your wonderful comments. I really appreciate them. You know, we all need corrected once in a while, and we all need some help in learning. So thank you, guys. I appreciate it. Take care. Bye-bye.